Greetings, and welcome to All Things Physics, where we carry out in-depth investigations of the physical world. Today I want to talk about orbiting objects, like Earth orbiting the Sun or the Moon orbiting Earth. Specifically, I want to investigate whether it's possible for one object to orbit another in such a way that the shape of the orbit is a square. Now, I realize your first reaction might be, no way, that's just crazy. But it turns out to be easier than you might think. It's well known that a planetary orbit takes the shape of an ellipse, a consequence of the gravitational attraction between the two objects. Therefore, it might seem obvious that a square orbit would be impossible. And this is certainly true if we're only dealing with two objects. But what if we include a third object? For example, we know the Moon orbits Earth and the Earth orbits the Sun, but have you ever thought about the shape of the Moon's trajectory around the Sun? Might it be possible for a moon to be orbiting a planet in such a way that its trajectory around the star is actually in the shape of a square? This is precisely the question I want to address in this video. Our story begins by taking a closer look at the Sun, Earth, and Moon. The Sun has a radius of over 400,000 miles. By comparison, Earth's radius is only around 4,000 miles, while the Moon's radius is about 1,000 miles. Of course, the Sun is 93 million miles from Earth, so when we see it in the sky, it looks quite small. If we zoom out far enough so that we can see the entirety of Earth's orbit, then both the Moon and Earth are too small to be seen. But the Moon orbits Earth at a distance of around 240,000 miles, so if the Earth-Moon system were a single object, it might just barely be visible at this scale. For our analysis, we're going to assume that both the Moon and Earth have circular orbits, with Earth having an orbital period of 365 days and the Moon having a period of 27.3 days. As a reminder, the orbital period is the amount of time it takes for an object to undergo an angular displacement of 360 degrees, or 2 pi radians. Here, we want to focus our attention on the Moon's trajectory around the Sun. Unfortunately, when viewed from afar, we can't really make out what's happening. Zooming in, we can see that as the Moon orbits Earth, its trajectory crisscrosses back and forth across Earth's path. Interestingly, even though the Moon circles around Earth, notice that its trajectory does not contain any loops. Many people find this fact quite surprising. In addition, at the end of a year, we find that the Moon's trajectory around the Sun does not form a closed path. In order to form a closed path, the Moon would need to complete an integer number of orbits around Earth in 1 year, a condition that's extremely unlikely to arise by random chance. When all is said and done, the path of the Moon around the Sun looks almost exactly like a circle, which, as should be plainly obvious, does not resemble a square at all. Let's now consider a fictitious star-planet moon system. The sizes of the objects will no longer be drawn to scale, but the distance scales will remain accurate. We'll continue to assume circular orbits for both the planet and the Moon, but we'll allow ourselves the flexibility to alter the orbital radius of the Moon and its initial phase. We'll adopt the same mass structure as the Sun-Earth-Moon system so that the mass of the star is much larger than the mass of the planet, which is much larger than the mass of the Moon. In addition, we'll assume that we can treat the planet-Moon subsystem as separate from the star-planet subsystem, a reasonable assumption as long as the Moon's orbital radius is not too large. Now, Kepler's third law relates the square of the orbital period to the cube of the orbital radius, but there are no constraints on either of these quantities. Therefore, we have complete freedom in choosing the Moon's orbital radius. Then, by adjusting the mass of the planet, we can dial in any orbital period we'd like. Of course, If we want the moon's trajectory to form a closed path around the star, then we need to choose the orbital period so that the moon completes an integer number of orbits around the planet each year. Stated another way, the moon's orbital frequency around the planet must be an integer multiple of the planet's orbital frequency about the star. We start with a fairly small orbital radius and a period similar to that of our own moon, but tweaked just a bit so that it forms a closed orbit about the star. Specifically, we'll assume the moon orbits the planet 13 times per year, an orbital period of just over 28 days. By design, the orbit of this moon is quite similar to our own, but due to the larger orbital radius, we can now easily see the trajectory crisscrossing back and forth across the planet's trajectory. Interestingly, as we increase the orbital radius, we begin to see the development of cusps that give rise to loops. Such a looping orbit is the kind of thing most people expect to see from our own moon's orbit around the Sun. But clearly, such an orbit is only observed if the moon's orbital radius is quite large. Although not central to our main purpose, it's worth taking a brief aside to determine the condition under which the trajectory will exhibit such loops. But first, there's a potentially confusing point that needs to be addressed. As mentioned, we've assumed the moon orbits the planet 13 times per year. But if you look carefully at the moon's trajectory, you'll see that there are only 12 loops in the orbit. To understand this strange behavior, let's examine the moon's orbit more carefully. Initially, the moon is aligned with both the planet and the star, and is at its maximum distance from the star. This is the geometry of a full moon. Once the moon has completed an angular displacement of 2 pi radians, the planet has undergone an angular displacement we'll call alpha. This orbital period is referred to as the sidereal period, and when referring to a moon's orbit, it's often called a sidereal month. Notice that at this point in the trajectory, the moon is not aligned with the planet and the star. However, a little while later we will once again reach the geometry of a full moon. At this point, the moon has undergone an additional angular displacement we'll call beta, and which is equal to the total angular displacement of the planet. The orbital period from full moon to full moon is called the synodic period. This is the time it takes the moon to return to the same point in its orbit with respect to the planet and the star. In the situation shown here, where the orbital motion of the moon and the planet are in the same direction, the synodic period is larger than the sidereal period. But notice that the moon's trajectory around the star is associated with the synodic period and not the sidereal period. To determine how the sidereal and synodic periods are related, we can equate the ratios of angular displacements of the moon to the planet. Then, performing a little algebra, we can determine how the angles, alpha and beta, are related. And if the moon completes an integer number of orbits around the planet each year, as we have assumed, then the angle alpha is given by 2 pi divided by this integer. Substituting this into the equation we just derived, we find that beta is then given by 2 pi divided by the next largest integer. Thus, if the moon orbits the planet 13 times each year, it will only go through 12 complete full moon cycles, exactly as we have observed. Returning to the question of looping orbits, let's choose the orbital radius to be the value just before loops appear and examine the moon's trajectory. You might find that this situation looks vaguely familiar. If we add in a circle, then it should become clear that this trajectory is identical to the trajectory of a point on the periphery of a wheel that rolls without slipping on the outside of this circle. Such a trajectory is called an epicycloid, and it's quite similar to a curve you may have seen before. As discussed in a previous video, a wheel that rolls without slipping is subject to a constraint that relates the translational speed of the wheel as a whole to the rotational speed about the center. On a flat surface, a point on the periphery of such a wheel traces out a curve called a cycloid. But what does the trajectory of a different point on the wheel look like? For example, suppose we look at the trajectory of a point that's inside or perhaps even outside the edge of the wheel. For a point that's outside the wheel's edge, you have to imagine that it rotates as if it were part of a larger wheel. Notice how similar these curves look to the moon trajectories we just determined. In fact, if we trace out the paths for similar points on a wheel that rolls on the outside of a circle, we get curves that are identical to the moon trajectories we already found. Personally, I find it quite intriguing when two seemingly unrelated phenomena, in this case a rolling wheel and a moon's trajectory around a star, turn out to be so intimately connected. The radius of a rolling wheel can be found by invoking the rolling without slipping constraint. Here, v is the speed of the wheel's center of mass, r is the wheel's radius, and omega is the rotational speed of the moon around the planet. In this situation, the speed of the wheel's center of mass is simply the speed of the planet, which we can write in terms of the planet's rotational speed about the star and its orbital radius. Equating these two speeds then allows us to solve for the wheel's radius, which turns out to be inversely proportional to the number of times the moon orbits the planet each year. For the situation we've been discussing, we can use n equals 13 to determine the specific value for the wheel's radius, as well as the radius of the circle the wheel is rolling around. Interestingly, notice that the rolling without slipping constraint equates the speed of a point on the periphery of the wheel to the speed of the center of the wheel. But the speed of a point on the wheel's periphery is simply the orbital speed of the moon, and as already mentioned, the speed of the center of the wheel is the orbital speed of the planet. In other words, the moon's trajectory around the star is in the shape of an epicycloid when the orbital speeds of the planet and the moon are equal. Thus, in order for the moon's trajectory around the star to contain loops, the moon's orbital speed about the planet must be larger than the planet's orbital speed about the star. At this point, we have all the background information we need, so it's time to focus on our main goal of searching for an orbit in the shape of a square. To obtain a trajectory that matches the fourfold symmetry of a square, we need to choose n equals 5. And then it's simply a game of varying the moon's orbital radius and its initial phase. As it turns out, the initial phase only ends up changing the orientation of the final pattern, so we'll choose a value that leads to the orientation of the square shown here. We're then left with a situation in which there's only a single parameter to adjust, the orbital radius. Shown here are the moon's trajectories around the star as the orbital radius is increased. If you're a true optimist, you might argue that one of these orbits looks a little bit like a square. However, if we're being honest, I think it's fair to say that even the squarest of these orbits looks much more like a circle than a square. If this is the best we can do, then our story has come to a truly unsatisfying end. However, there's one last thing we can try before giving up: changing the direction of the moon's orbit. Up until now, we've assumed that the moon's orbital motion is in the same direction as the planet's. In our case, we've been assuming they both orbit counterclockwise. Although this behavior is typically what's observed in nature, there's certainly no law requiring that this be the case. So let's reverse the direction of the moon's orbit and see what happens. Interestingly, when the moon's orbital motion is opposite the planet's, the synodic period is smaller than the sidereal period. Therefore, in order to obtain a pattern with fourfold rotational symmetry, we now need to use n equals 3 instead of n equals 5. You can convince yourself this is true using an argument similar to the one I used previously. It's not terribly difficult, so I encourage you to work through the details. Once again, the moon's trajectories around the star are shown as the orbital radius is increased. Clearly, the situation has improved. In fact, I think it's fair to say that even a true pessimist would have to admit that we've now found an orbit that looks significantly more like a square than a circle. Now that we've constructed a nearly square orbit, the last thing we need to do is examine whether such an orbit is actually possible. For the orbit shown here, I've listed the specific values used for the Moon's orbital radius and period. Recall that one of our assumptions involved the masses of the star, the planet, and the Moon. However, we had to adjust the planet's mass to get this specific combination of the Moon's orbital radius and period, so we need to check that our assumption is still valid. Using Kepler's third law, once for the star-planet subsystem and again for the planet-moon subsystem, we can determine an expression for the ratio of the planet's mass to the star's mass. Substituting in the Moon's orbital parameters, we see that the planet's mass is indeed much smaller than the mass of the star. Furthermore, the Moon's orbital parameters depends only on the mass of the planet, so we are free to choose the Moon's mass to be much smaller than the planet's mass. We also assumed that we could treat the planet and Moon as its own subsystem, without including the effect of the star. In order for this assumption to hold, the Moon's orbital radius must lie inside the region of space in which the planet dominates the attraction of satellites, a region known as the planet's Hill sphere. Thus, in order to have a stable orbit, the Moon's orbital radius must be smaller than the radius of the planet's Hill sphere. Solving for the ratio of the planet's mass to the star's mass, and again making use of Kepler's third law, we arrive at an expression showing that the Moon's orbital radius is definitely smaller than the Hill radius. Having verified our assumptions, it should now be clear that, given the right conditions, the square orbit shown here is a valid trajectory for a moon about a star. I hope you're impressed with how easy it is to construct a reasonably square orbit. And given that there are 100 billion galaxies, each containing 100 billion stars, it's almost certain that the orbit shown here exists somewhere in the universe. Still, I imagine there are at least some viewers wondering if we can do even better. I mean, the orbit shown here is not truly a square, and we created it using only 3 objects. What if we used 4, 5, or even more objects? Might we end up with an orbit that looks even more like a square? This is an excellent question, and one that's certainly worth pursuing. Unfortunately, this video has already gone on long enough, but I'll return to this issue in a future video. I'll let you in on a little secret though. The answer turns out to be truly mind-blowing, so be sure to check back soon. Until then, I'm David Jackson, and this is All Things Physics.